Good day. We are going to continue our discussion on the probability theory. For this time, we are going to discuss the combinatorial problems. We consider a class of problems in which the assignment of probabilities can be made in a natural way. So, let the sample space be a finite or countably infinite set, and let F consist of all the subsets of the sample space. For each point, in this set, belongs to the sample set where I is equal to 1, 2, and so on, aside non-negative numbers p sub I with the summation of the p sub I is equal to 1. If set A is any subset of the sample space, let the probability of A is equal to the summation of p sub I belongs which is a point within the set that belongs to the sample set. Then it may be verified that the probability, or P, is a probability measure, where P is the probability of the sample set is equal to the probability of the point within the sample set. And the probability of any event A is found by adding the probabilities of the points of the sum of the set A. And the triple, the sample space, the F, and the probability of this type is called the discrete probability space. Let's start to have an example. Throw a biased coin twice. The information about the experiment is shown in the figure. Find the probability of getting at least one head and find the probability of getting tail on the first toast. Okay, so let's start to have the first problem. Find the probability of getting at least one head. So for our solution, let our E sub 1 be the set. The event A sub 1, E sub 1 is um, the set of at least one head. Okay, now in this case, from the given, we have one head, at least one head. We have the A sub 1, then we have the A sub 2, and then we have the A sub 3. So in this case, our E sub 1 is equal to our A sub 1 union to our A sub 2 union with our A sub 3, because these are the sets in which at least one head, in the experiment. In other words, the probability of E sub 1 is equal to the probability of A sub 1. Since this is union, so you have plus the probability of A sub 2 plus the probability of A sub 3. So in this case, the probability of A sub 1 is equal to 0.36, and the probability of A sub 2 is equal to 0.24. And then the probability of A sub 3 is equal to 0.24. Add them all, that's equal to 0.84. So in other words, the probability of getting at least one head is 0.84. That's our final answer. Now let's find the probability of getting tail on the first toast. So in this case, our uh, our E sub, for the solution, our E sub 2 would be the set of which at least, not at least, tail on the first toast. This is tail on first toast. So in this case, this would be um, a sub 3 union with a sub 4. Okay, so we have this one. So, in other words, for our solution, we have uh, our a sub 3 is equal to 0.24. Wrong. Since the question is probability, then we are going to, okay, have the probability of e sub 2, which is uh, events in which tail came first, okay, after the toast, is equal to the probability of a sub 3 plus the probability of a sub 4, which is equal to 0.24 plus 0.16, which is equal to zero point 0.4. And that is our final answer. Okay, so very easy. Special case where the sample space is equal to the sets, okay, and p sub I, okay, is equal to 1 over n, where I is equal to 1, 2 up to n. We have the probability of A is equal to the number of points of A over the total number of points in the sample space, which is thus the same with the favorable outcomes over total outcomes, corresponding to the classical definition of probability. Therefore, in this case, finding the probability of A simply involves counting the number of outcomes favorable to the set A. When the n is large, counting by hand may not be feasible. Combinatorial analysis is simply a method of counting that can often be used to avoid writing down the entire list of favorable outcome. In this case, there is only one basic idea of the combinatorial analysis. So let's have the next slide. So the idea is that suppose that a symbol is selected um, from the set, you have a sub 1 up to a sub n. If a sub I is chosen, a symbol is selected from the set uh, b sub I1 up to b sub im. Each pair of the selections, we have a sub I, b sub ij, is assumed to determine a result of the function of the ordered pair ij. If all the results are distinct, the number of possible results is the product of mn or nm. Since there is a one-to-one correspondence between the results and pairs of integers ij, or I is equal to 1 to n and j is equal to 1 to m. If after the symbol b sub ij is chosen, a symbol is selected from the set c sub ij2 1 up to c sub ijp. In each triple, a sub I, b sub ij, c sub ij key determines a distinct result of the function of the triple I, j, and k. The number of possible results is m, n, nmp. Okay. Analogous statements may be made from for any finite sequence of selection. So certain standard selection occur frequently, and it is convenient to classify them. Let's say a sub I up to a sub n, okay, should be distinct symbols. Okay, so let's have order sample of size r with replacement. So you have here the number of ordered sequences a sub I1, a sub I sub 1 up to a sub I sub r, where the a sub I sub k belongs to the set a sub 1 up to a sub n, is n by n by n up to n or r times. Or, in other words, this is n raised to r. Okay, so take note that the term with replacement refers to the fact that if the symbol a sub I sub k is selected at any step k, it may be selected again at any future time. So for example, okay, the number of possible outcomes. So for example, okay, example, okay, so let's say um three dice, okay, are thrown. So if three dice are thrown, then the there is uh 6 times 6 times 6, which is equal to 1 to 6 samples rather. Okay, so that's the concept. Next. Okay, the number of ordered sequences a sub I sub 1 is up to a sub I sub r, where the a sub I sub k belongs to the set a sub 1 up to a sub n. But, okay, repetition is allowed. Uh, no a sub I can appears more than once in the sequence. Okay, so in this case, uh, we have the n times n minus 1 up to n minus r plus 1 is equal to the n factorial over n minus the quantity n minus r factorial, where r is equal to 1, 2, up to n. Um, the first symbol may be chosen in n ways, and the second in n minus 1 ways. Since the first symbol may not be used again, and so on. So the number is this one. Okay, the form is okay. Um, this is called number of permutations of our objects out of n. Okay, which can be, of course, in our college days. This is also known as uh, we have this one, and okay, like something like this one. So this is a permutation of our objects out of n. Okay, so for example, let's say three digits number, okay, can be formed from 1 to 9. Okay, if no digit can be repeated. So this is for example. Okay, if there would be no repetition is allowed, then we have 9 times 8 times 7, which is equal to 504. Or if we are going to use this formula, then you have the 9 factorial. Okay, 9 factorial over you have 9 minus 3 factorial, which is equal to 9 factorial, okay, over you have um, 6 factorial, which is equal to 9 times 8 times 7, which is again equal to 504. So that's it. So let's have unordered samples of size r without replacement. Okay, So the number of unordered set a sub I sub 1 up to a sub I sub r, where the a sub I sub k and k is equal to 1 to r are distinct elements of the set a sub 1 up to a sub n. Okay, so for example, we have the numbers of the way selecting are distinct objects out of n. If order does not count, so we have this formula. You have um, this one. So n taking r at the time is equal to n factorial all over uh, r factorial times the quantity n minus 1, n minus r factorial. Okay, so to see this, we are going to consider two processes. The first one is select r distinct objects out of n without regard to order. Okay, this can be done in uh, n uh, and objects taken are at a time ways. Okay, where uh, this one should be determined, and then the second is for each sex selected. Okay, let's say a sub I sub 1 up to a sub I sub r. Okay, select an ordering of a sub 1 sub a sub I sub 1 up to a sub 1 sub r. Okay, so this can be done in uh, r taken r at a time, which is equal to r factorial ways. Okay, now the result of performing these steps is actually a permutation of r objects out of n. So we could have this formula. You have um, n r times r factorial, which is equal to uh, n objects taken r at a time, which is equal to n sub n factorial over the quantity n minus r factorial. So which is a permutation or a combination. So you have the combination of n objects taken r at a time is equal to, so you have this one, n factorial or over r factorial times the quantity n minus r factorial. We have to define that uh, n objects taken 0 at a time is equal to n factorial over 0 factorial uh, times n factorial, which is equal to 1, to make the formula for the combination of n objects taken r at a time valid for uh, r is equal to 0 up to n. Okay, so that's it. Okay, next we have an ordered sample of size r with replacement. Okay, so we wish to find the number of an ordered set from a sub I sub 1 up to a sub I sub r, where the a sub I sub k belongs to the set a sub 1 up to a sub n, and repetition is allowed. As an example, let n equals 3 and r is equal to 3. Okay, let the symbols be 1, 2, and 3. List all the arrangements in the column, okay, so that A precedes B if and only if A reads as the ordinary 3-digit number is less than B. In an adjacent column, list all the new sets of sequences formed from the old by adding 0 to the first digit, 1 to the second digit, and 2 to the third digit. Okay, so according to this problem, we are going to list down. So let's try to list. So what are those numbers? Okay. So we could have 1 1 1, and then you have 112, 113, 122, then 123, then 133. You have 222, 2, 223, 233, and 333. Now, these are the numbers, okay, in which A precedes B. Okay. Now, it is in the instruction, we have also to list a new set of sequences formed by the old by adding 0 to the first digit, then 1 to the second digit, and 2 to the third digit. So in other words, in this case, so we have 1, 2, 3. Then this is 1, 2, 4. Then 1, 2, 5. Then 1, 3, 4. Then you have 1, 3, 5. Then 1, 4, 5. Then you have 2, 3, 4. Then you have 2, 3, 5. Then you have 2, 4, 5, and 3, 4, 5. Okay. So in the first column, we have unordered samples of size 3 out of 3. Okay. With replacement. Okay. In the second column, we have unordered samples of size 3 out of 5 without replacement. So in in this way, we can set up a one-to-one correspondence between unordered samples of the size r out of n with replacement and the unordered samples of size r, okay, out of n plus r minus 1 without replacement. Okay. Thus, the number of such samples can be expressed or can be written in uh, the combination of n plus r minus 1 taken r at a time. Okay, so that is our, this can be shown using this formula. Okay, so let's have an example. Find the probability of obtaining 4 of a kind in an ordinary 5-card of poker hand. Okay, so for our solution, okay, there are a combination, okay, of 52 cards taken 5 at a time, okay, which are distinct poker hand, uh, without regard to order. And so we may take the sample space to have 52 out of 5 points. Okay, so to obtain the number of hands in which there are 4 of a kind, we have to choose the face value to appear 4 times. So there are 13 choices. We have the ace, we have the king, we have the queen up to 2. Then we have to choose the fifth card, which can be expressed in 48 ways. Okay, so take note, we have 13 choices. So 13 choices, and then there are 48 ways in choosing the fifth card. So in other words, for our solution, okay, the probability is equal to, you have 13, okay, because there are 13 choices out of not 13 choices times 48 ways on finding the fifth card over, okay, you have you have the sample space. The sample space is 52 taken 5 at a time. Okay, so we have here, you can use calculators. So in this case, 13 times 48 is equal to 624. Then we have here the combination of 52 taken 5 at a time, So you have 2,598,960. So in other words, if we are going to reduce that one, okay, we have the probability is equal to 1 over 4,165. Okay, or that is approximately equal to 0.00024. Okay, so that's the probability of obtaining four of a kind in an ordinary five card poker hand. Okay, next. Um, Three balls are dropped into three boxes. Find the probability that exactly one box will be empty. Okay, so in this case, um, in in problems of dropping our balls into n boxes, we may regard the boxes as distinct symbols of a sub 1 up to a sub n. And then each toes of a ball corresponds to the selection of the box. Thus, in this case, we have the sequence of, okay, uh, you have a sub 2, a sub 1, a sub 1, a sub 3. Okay, corresponding to the first ball into the box 2, and then the second and the third into box 1, and the fourth into the box 3. Okay, because uh three boxes. Okay, now um in in general, the arrangement of our balls in n boxes corresponds um, to the sample of size r from the symbol a sub 1 up to a sub n. Um, if we require that the sampling um, be with replacement, this means that the given box can obtain any number of balls. So sampling without replacement means that the given box cannot contain more than one ball. If we consider ordered samples, we are saying that the balls are distinguishable. Okay. Uh, for example, we have one ball into box 3, or ball 1 into box 3, then ball 2 to box 7. Okay, for example, which is different from ball 1 to box 7 and ball 2 to box 3. In other words, we may regard the balls as being numbered 1 to up to R. Okay. An ordered sampling corresponds to the distinguishable balls. Okay. If there is no restriction on the numbers of balls in the given box, the total number of arrangement, taking into account the order in which the balls are tossed, okay, which regarding uh, the balls as distinct, so it is the number of ordered samples of size R from a sub 1 to a sub n with replacement, or it can be solved using the concept of n raised to r. If the boxes are energy levels in physics and the volts are particles, then we have to use the concept of Maxwell Boltzmann assumptions or assumption. Um, that is, all n raised to r arrangement are equally likely. Um, if there can be at most one ball in the given box, the number of arrangement would be the permutation of n taken r at a time. If the order in which the balls are tossed is neglected, we are simply choosing our boxes out from n to be occupied. And that is the Fermi-Dirac assumption. Okay, takes the combination of n taken r at a time, which is the possible selection of boxes, or the energy level as equally likely. Okay, we might also mention the Bose-Einstein assumption. Here, a box may contain an unlimited number of balls, but the balls are indistinguishable. That is, the order in which the balls are tossed is neglected, so that, for example, you have a sub 2, a sub 1, a sub 1, a sub 3 is identified with a sub 1, a sub 3, a sub 1, a sub 2 because they are uh, indistinguishable. Thus, the number of arrangement counted in this scheme is the number of unordered samples of the size r with replacement. Okay. Or simply the concept that is presented in the previous slide, you have the combination of n plus r minus 1 taken r at a time. So the Bose-Einstein assumption takes all these arrangement as equally likely. So to answer the original this problem, we have boxes a sub 1, a sub 2, and a sub 3. Okay. And the sequences of length 3. So because we have 3 balls that is being tossed. So in other words, we take all 3 raised to 3. For our solution, we have 3 raised to 3, which is equal to 27. So there are 27 ordered samples with replacement as equally likely. Now we have, you know, the probability, okay, of exactly one box empty is equal to the probability of box 1 empty, box 2 empty, box 2, and 3 occupied, plus the probability of box 2 empty, box 1, and box 3 occupied, plus the probability of box 3 empty, okay, you have the box 1 and 2 occupied. Okay. So let's try to continue. Furthermore, um, we could also say that the probability of uh, box 1 empty, uh, box 2 and 3 occupied is equal to the probability of we have a sub I does not occur in the sequence. Okay, does not occur. Okay, in the sequence uh, a sub I sub 1, a sub I sub 2, a sub I sub 3, but a sub 2 and a sub 3 both occur. Okay, so if a sub 1 does not occur, either a sub 2 or a sub 3 must occur twice and the other symbol once. We may choose a symbol that is to occur twice in two ways. The symbol that occurs once is then determined. Say a sub 3 occurs twice and a sub 1 once. The position of a sub 2 may be any of three possibilities. So the position of two a sub 3s is then determined. Thus, the probability that box 1 will be empty and boxes 2 and 3 occupied, okay, is equal to uh, 2 times 3 over 27. Okay. So, in other words, this is equal to 2 times 3 over 27. Okay, or 6 over 27. So, the probability that exactly one box will be empty is by symmetry. That is three box, not but because this is by symmetry. Two, no, no, no. It must be, so the probability uh, of exactly one box will be empty is equal to 3 times 6 over 27, which is equal to 2 over 3. And that is our final answer. So that's all the presentation for the combinatorial problems. Thank you for listening.